Okay, let's take a look at building linear models as we continue to talk about linear functions. So our objective, we want to build and analyze linear models from verbal descriptions, from real world situations, okay? So what do we know that's going to help us here? We know what a linear function is, okay? It's a function of the form f of x equals mx plus b. And of course, m stands for the slope or the average rate of change, which we know from a previous video lecture is a constant. There's a constant average rate of change when it's linear. And the b stands for the y-intercept. All right, when it comes to building a linear model from actual or from real-world data or real-world information, this generally means two things we want to keep in mind. Number one, we're talking real life here, real world, so we're almost always going to be in quadrant one, the positive quadrant. So we're going to have a positive domain of some sort, and we're going to have a positive range of some sort in general. Okay, we're going to be from 0 to positive infinity or from 0 to some number in both cases. And number two, because it's a real world example, we can interpret our slope and it has meaning if we use the labels. And generally we describe our slope as follows when we interpret it. For each additional x unit, whatever that might be, the y unit, again, whatever that might be, increases or decreases by some amount. Okay, so we can interpret our slope and it has meaning because of the real world situation that we're in. Let's take a look at two examples. Our first example, we'll take a look at a basic linear cost function. In fact, I'm going to write that up here. I probably should have put it next to example one. This is a linear cost example, okay? So example one has to do with linear cost. Suppose that a small bicycle manufacturer has daily fixed costs of $1,800, and each bicycle costs $90 to manufacture. Okay, let's come up with a linear model that expresses the cost C of manufacturing X bicycles in a day. Well, I know what the linear model is. Okay, it's going to be C of X equals mx plus b. That's my linear model, our linear equation, our linear function. So what is our slope? Well, it's $90 per bike. So C of X is $90 times X. You're manufacturing X bikes a day, so every bike costs $90. And our fixed cost, so our y-intercept, is $1,800. Okay, so let's take a look at this, okay? If we manufacture no bicycles, the cost of 0 bicycles, okay, we're going to have, what's it going to cost us? It's going to cost us $1,800 because no matter what, we have to pay for the building, the lights, etc., and our employees. If we manufacture no bikes, we still have to pay our fixed costs, okay? And then for every bike we manufacture, it costs an additional $90. So if we manufacture one bike, it's $1,800 plus 90 times 1. If you manufacture 2 bikes, it's $1,800 plus 90 times 2, etc. Okay, letter B, what's the assumed domain? Okay, well, our x-axis is the number of bicycles. Okay, so our assumed domain is that our bikes can go from 0, well, they could go to infinity, I guess. So I would say in set notation, the number of bicycles, all x's, such that, well, it's going to be greater than or equal to 0. We certainly aren't going to manufacture a negative number of bicycles. And depending upon the number of people we have, I guess we could conceivably go to infinity. We might choose to cap this off depending upon other information. But our domain, assumed domain, is we're talking positive numbers of bicycles or 0. We might have 0 bikes that day. So basically we're saying greater than or equal to 0. Now, of course, you can't go to infinity, but we're going to assume that our domain is going to be greater than or equal to 0. Okay, let's interpret that slope. Okay, the slope is 90. So let's go back over here and talk about interpreting the slope. For each additional x unit, for each additional bicycle, okay, the y unit, the total cost increases or decreases by some amount. Okay, so interpret our slope. Our slope is equal to 90. Okay, so for each additional bike, that's our x unit. Our x unit is bikes. Okay, the y unit, cost of manufacturing. This is the y, the cost of manufacturing. The cost of manufacturing. This is our y unit. Okay, it's a positive slope, so it increases. Okay, so it increases. Positive slope means we're increasing. For each additional bike, the cost of manufacturing increases $90. Okay? So that's interpreting our slope. For each additional x unit, the cost, the y unit, in this case, x is number of bikes, c is cost of manufacturing. The cost of manufacturing increases by this number, $90. Let's graph this. Okay, we're going to graph this using our graphing device. So let's go into here, and I can see my equation that I want to graph right up here. I'm not sure what's in my calculator. Let's clear that out of there. 90 times x plus 1800. Okay, let's see how that's going to look. I'm going to need to change my window, I'll bet, a lot because of how this is going to work. So I'll first go to the standard window, and you'll notice that we're not going to see anything. Okay, we see nothing because when we have 0 bikes, the cost is 1800. So first thing, window, I want to be in my first quadrant. So 0. Okay, my number of bikes is going to go from 0 up. Let's go from 0 to 100. Let's say we could produce up to 100 bicycles. Let's just take a look at the window 0 to 100. And I'll count this out by tens. Why not? So I'll label my axes every 10. My y, of course, starts at 0. Well, hang on a second. Well, we'll go from 0, but we know if I make 0 bikes, it costs $1,800. So I better max out pretty high. I'm going to max out at 2,500 just to see it. Okay, I know I start at 1,800, and I'm going to count this off by 500s. Let's graph that. Whoops, that didn't do much for me there. You can see I'm only have a little bit in the corner there. So let's go back to my window. Looks like I need to, let's max out my y at 5,000. And I'll count by thousands. Let's see if that helps me. There we go. That's a little better. Okay. So you can see here, 0 bicycles. If I press calculate, if I calculate my value, so 1, and I say I want 0 bikes, I have an $1,800 cost, and that makes sense. That's my fixed cost. And as I go up, I'll go back to the second calc value. Okay, 1 bike, $1,890, 2 bikes, $19.80. I'm working my way up, and you can see that each additional bike is going to cost me $90. Okay, each additional bike. And you can see again my domain. I could, you could go on, you can keep making bikes. I don't know how many you could make, but obviously I'm focused on the positive number of bikes and positive cost. Okay. Let's take a look down here. We're going to use our graph for this. We'll do this both ways, graphically and algebraically. What is the cost of manufacturing 14 bicycles in a day? Okay, well, the cost, C of x, is equal to 90x plus 1800. We know that from above. Okay, from letter A, that's right here. That's this equation. Okay, let's see here. But I want to manufacture 14. So I'm going to put 14 into my function, which means wherever I see x, I'm going to replace with the number 14. And then I'm just going to pull out my calculator. So I'm going to quit out of the graph. 90 times 14, and then I'm going to add on the $1,800 fixed cost. $3,060 is what it's going to cost me right here to manufacture 14 bicycles in a day. Okay, let's take a look. Okay, let's go back to the graph. Here's my graph. Okay, let's see. Let's go to second calc. I want a value. I want to manufacture 14 bikes. So I'll put x equals 14 and press enter. And sure enough, $3,060 is a point on my function. It's what it's going to cost me to manufacture 14 bikes. Okay, the second question here is, hey, how many bicycles can be manufactured or could be manufactured for $3,780? $3,780. Well, here's my cost function. The cost for x number of bikes is 90 times x plus 1,800. Well, I want that to equal 3,780, and that equals 90 times x plus 1,800. Well, let's first subtract 1,800 from both sides. Okay, and so I need to pull my calculator out. What is 3,780 minus 1,800? Whoops, 3,780 minus 1,800. And I've got 1980 equals 90 times x. I'm running out of paper. Divide both sides by 90. Okay, I'll divide that number by 90. And it looks like, I'll come over here because I'm out of space. The number of bikes is 22. I can manufacture 22 bikes for $3,780. Okay, again, let's take a look at this in our calculator on the graph. Okay, so let's go back and let's go back to my graph. Okay, I can estimate this with my trace key. Okay, I want to. How much for 3,780? So one way to do this is to go to second trace. Whoops, let me clear this. Sorry about that. Go back to my graph. Let's press my trace key, and I want my y value to be 3,780. And I'm going up, and looks like I'm between here. This is 3,743, and here this is 3,811, and I've got 22 to 21. So it's between 21 and 22 bicycles. That gives you an approximation. The other way to do that says, let's go back to the y equals, and let's put, I want y2 to equal 3,780. Okay, and where those two lines intersect is going to be the number of bicycles where those two equations are the same. So, second calc, the intersection, number 5. Okay, first line, second line, take a guess. Sure enough, 22 came up right here. 22 bikes cost $3,780 to manufacture. Okay, let's look at a supply and demand example. A fair amount of writing in this one because there is some vocabulary to take a look at. The problem's not that complicated, but kind of getting some vocabulary in there is important. Okay, so just some definitions. The quantity supplied of a good is the amount of a product that a company is willing to make available for sale at a given price. Okay? The quantity demanded of a product, of a good, is the amount of a product that consumers are willing to purchase at a given price. So a couple of definitions: quantity supplied, quantity demanded. Okay, suppose the quantity supplied, given by the letter S, and the quantity demanded, given by the letter D, of cell phones each month are given by the following two functions. Okay, P is the price in dollars of the cell phone. So the supply, the quantity supplied depends on the price, and it equals 30 times the price minus $900. The quantity demanded depends on the price, and it equals negative 7.5 times P plus 2,850. Okay, so we have these two linear functions, a supply function and a demand function. Okay, letter A. Okay, the equilibrium price of a product is the price at which supply equals demand. If any of you have taken a little bit of economics, you'll know that supply equals demand gives you the equilibrium. Determine the equilibrium price and the amount demanded or supplied at that price. We want supply to equal demand. So we want supply to equal demand. Okay, well, supply is 30 times P minus 900. Okay, demand is negative 7.5 times P plus 2850 according to the functions we were given. We want those two to be equal. Okay, determine the price. Well, this is one equation in P. Let's get our P's together. I think I'll add 7.5 P to both sides because I like to keep my variable term positive. I'll add 900 to both sides as well. So I'm shifting my variable term to the left and my constant term to the right. So this is pretty simple. 30P plus 7.5P is, whoops, I say it's simple, and then I proceed to write it down incorrectly. Is 37.5 times P, and 2850 plus 900, I think, is 3750. I'm going to double check that with my calculator. 2850 plus 900, yes, 3750. Now let's divide both sides by 37.5 so that P is by itself. And I can do this. This gives me 100. So at a price of 100, that's the equilibrium price is 100. Okay? Equilibrium price is 100. Okay, I'll tell you, let's see here. So this to find equilibrium price. This question then says, hey, determine the price, I did that, and the amount demanded or supplied. Okay, well, I can pick either one of these to get the amount demanded or supplied because I know they're equal. So I'll choose choose either S of P or D of P to find the amount, which is number of phones. Okay, I'll choose S. So S of P is equal to 30 times P minus 900. Well, I want to know the supply amount when the price is 100. So I'm going to replace P with 100 minus 900 and something. Let's see, I pull my calculator out. 300 times 100 minus 900, and I got a number I think that's not correct. Let's see what I missed here. Oh, all right, there's my mistake. You probably caught that, didn't you? 30 times P, not 300 times P. Let's try that again. 30 times 100 minus 900. And the supply is 2,100 cell phones at the price of $100 per. Okay? Let's take a look at this on our calculator. Okay, so I'm going to go to y equals. Let's see, with the equilibrium price is where the two lines intersect when they're both equal. So I'm up here, I can see my two linear functions. They're right up here on my paper. Let's go back and clear out the previous example. I'll choose S of P to be y1, so 30 times x minus 900. I'll choose my demand function to be y2, negative 7.5 times x plus 2850. I'm going to guess that I'm going to, well, I'll tell you what, we know we're in the first quadrant because this is real. I'm going to go to zoom, and in my calculator, I'm going to choose quadrant 1. And let's see if my quadrant 1 gets it to fit. And the answer is no. Okay, so let's go to my window. Well, my quadrant 1 maxed out at 13. I know I need to go to at least 100. Let's go to 200 cell phones. And I'll count by 50s. And my Y, this is my cost. Certainly going to start at 0. I'm sorry, my X is my price, excuse me. My Y is the number of phones. Okay, so let's go to, I don't know, let's go to 1,000. And we'll count by a 100. Let's see if this works for me. Nope, I only got the first curve, so my other curve is somewhere else. Let's take a look here. Let's see. I'm curious this zoom. Let's try zoom fit. Some people talk about using zoom fit. Well, there we go. I just thought I'd take a stab at that. Oh, look at that. Zoom fit works great. I just used the zoom fit. So again, I went to zoom. In my case, I had to go down past number 9 to zoom fit, which told me to fit the graph. And out came this. So there's something for you. All right, I'm not sure what my window looks like. Let's take a look at how it set the window. This window goes from 0 to 100 and counts by 50s. This one maxes out at 5,100 and counts by hundreds. I could probably change that, but we'll leave it. Okay, equilibrium is the intersection, so let's calc the intersection, number 5. First curve, second curve, yeah, there's only one intersection. And sure enough, 100 is the price, remember X is the price, and 2,100 is the number of cell phones. And that's what we got right down here, a price of 100 and 2,100 cell phones. Okay, second question with this one. Determine the prices for which quantity supplied is greater than quantity demanded. Okay, so I want my quantity supplied, S of P, to be greater than my demand. Supply greater than demand. Okay, supplied greater than demanded. Okay, S of P, if you'll recall, 30P minus 900. So S of P is 30P minus 900 greater than quantity demanded. Negative 7.5P plus 2850. Negative 7.5P plus 2850. It's an inequality, but we still solve it just like we would solve an equality, recognizing that if we multiply or divide by a negative, the inequality reverses. So I'm going to do exactly what I did last time. I'm going to choose to move my variable terms to the left to keep them positive, which means I'll move my constant term to the right. 37.5 times P is greater than 3750. We've already done all this. Divide both sides by a positive 37.5, so the inequality does not reverse. So when the price is greater than 100, okay, so price greater than 100, the quantity supplied is greater than the quantity demanded. Okay, let's see this on the calculator on our graph. Okay, so here's our graph, and you can see, let's go back to my y equals. My blue was my quantity supplied. That was my S. I want the blue to be above the red. Where's the blue above the red? It's above the red from this point. It's above when the number is greater than this point. We already know that point is at 100 because we found that. Second calc, intersect. Okay, we took a guess. We came up with 100. So when the price is greater than $100 per cell phone, the quantity supplied is going to be greater than the quantity demanded. Okay, so there you have it. Using some linear functions to model some situations. Again, keep in mind, we're always in the positive quadrant, and that the slope has meaning in these real-world situations.